In this video, the learner will determine if a figure has line symmetry or point symmetry in 2 dimensions, or plane or axis symmetry in 3 dimensions. We say a figure is symmetrical if there's a rigid transformation, such as a reflection, translation, or rotation, that maps that original figure onto itself. In 2 dimensions, there are 2 types of symmetry. There's line symmetry, which looks like this. If we were to reflect that figure up, it would map onto the figure on top. So if we were to fold that together along that line, those sides would look identical. Our next 2-dimensional symmetry is called point symmetry. This is when we take a figure and rotate it and it maps onto itself. So notice at 0, 90, 180, and 270, the figures look the same. For 3 dimensions, we have plane symmetry, which means we can use a surface to cut a 3-dimensional figure into 2 symmetrical pieces. So we're reflecting that figure across that surface. And axis symmetry, where we rotate a 3-dimensional figure around an axis of symmetry. First, let's look at line symmetry. This is when a 2-dimensional figure is mapped onto itself using a line of reflection. So as you can see in this illustration, that red triangle is flipping across to create that other red triangle. So this quadrilateral, the whole figure, is symmetrical about that line of reflection. We're going to look at a few examples. We're going to state whether the object appears to have reflectional symmetry. Reflectional symmetry is another name for line symmetry because we're using reflections to create that symmetry. We're going to write yes or no, and if so, copy the figure and draw all lines of symmetry and state their number. So in this first example, we have a crab, and there's 1 line of symmetry. We can only make that vertical line that makes those 2 halves look exactly the same. If we were to draw a horizontal line, the top half and the bottom half would not look the same. For part B, we have the starfish. The starfish has 5 lines of symmetry. This vertical line, this line, this line, this line, and this line. Where if we just took one of those lines, both halves would mirror each other. In part C, we have an oyster shell, and there is no line that I can draw on this figure anywhere that would create a symmetrical figure. There's no way to cut that directly in half where both halves look exactly the same. All right, here, state whether the figure has reflectional symmetry, write yes or no. If so, copy the figure and draw all lines of symmetry and state their number. In this first figure, this parallelogram, let's try drawing a few lines and seeing if that makes a line of symmetry. So if we were to draw this line and I folded that up, this corner would end up here, this corner would end up down here. They would not match up exactly, so that would not be considered a line of symmetry. If I were to draw this line, the same thing would happen. They wouldn't match up exactly. If I tried to draw a horizontal line, they wouldn't match up, or vertical line would also not match up. So this parallelogram does not have any reflectional symmetry. There's not a line of reflection that we can draw that creates the same image on both sides of that line. In this pentagon, we have 1 line of reflection that can be made. We can draw a vertical line from this vertex to the other side, and that would be a line of symmetry. Notice we wouldn't be able to do that with every single vertex, so that's our only line of symmetry. So yes, it does have reflectional symmetry, but there's only 1 line of reflection. In the rectangle here, we could draw a vertical line straight down the middle of that rectangle, and notice that both of those sides look exactly the same on each side of that line of reflection. We could also draw a horizontal line that creates reflectional symmetry in the rectangle. If I remove that other line, you can see that top half and bottom half look exactly the same. If I also remove this line, what if I tried a diagonal? Notice if I were to fold along that line of symmetry, that this corner would end up here, this corner would end up down here. They would not match up. Those sides do not mirror each other exactly. That's not to say that those two triangles would not be congruent, but they are not mirror images of one another. So we only have that horizontal line and vertical line of reflections here. So yes, we have reflectional symmetry, and we have two lines of reflection. Next, we have point symmetry. This is when a two-dimensional figure is mapped onto itself using a rotation. So notice this figure here. Starting from this position at 0 degrees, if we were to rotate that figure, notice how many times it looks like that original image. So we could say here, 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 and then back to normal. So we would rotate that 90 degrees, 180 degrees, 270 degrees, and all of those images look exactly like my original. So that would be an example of a figure having point symmetry. Another name for point symmetry is rotational symmetry, because we're using rotations to create that symmetry. There are a couple things we need to consider as we talk about point symmetry. The first thing is called the order. The order of a figure is the number of times in a full rotation that the figure maps onto itself. So when we start from here, we have 1, 2, 3, and then 4. So the order of this square is 4. We also need to consider what's called the magnitude. The magnitude of the figure, or the degree of rotation, is the smallest degree measure of a rotation that maps the figure onto itself. So we look and see as it's rotating, and where's the first time that it looks like itself again. So as we start here, 1, 2, and that would be a 90-degree rotation. So its magnitude would be 90 degrees. A way to think about it is we're going a full 360 rotation, and the order is how many times in that full rotation that it maps onto itself. So we could find the magnitude by dividing that 360 degrees by how many times it maps onto itself, and that would be equal to the magnitude. So notice that full rotation, we determined that this figure had an order of 4, so 360 divided by 4 gives us that 90 degrees. So as we already stated, this figure has an order of 4 and a magnitude of 90 degrees. We're going to state whether these figures have rotational symmetry. We're going to write yes or no, and if so, copy the figure and locate the center of symmetry and state the order and magnitude. Okay, so here we have a regular hexagon. We know that if we rotate this figure, we can get it to look like itself again. So as I rotate this figure, it looks like itself here 1 time, 2 times, 3, 4, 5, and we're back to 6. So in that full rotation, we were able to determine that this does have rotational symmetry and that its order is actually 6. We could determine the magnitude of that rotation by taking 360 and dividing by 6, or 60 degrees. The center is going to be the intersection of the diagonals, because we're actually rotating around the center of the figure. For this right triangle, as I start to rotate this figure, we are looking for when it looks like our original figure. So as I start to rotate it, you can see that it does not look like itself until we've made a full rotation. This means that this figure does not have rotational symmetry. So this would actually be a no. There's no rotation between 0 and 360 that maps that right triangle onto its original self. Here, if I look at this figure, if I start to rotate it, there's 90 degrees, and it doesn't look like itself yet. But as we look at 180 degrees, it does look like itself again. As I rotate back, we are back at our original figure. So it did look like itself one time in that rotation, and then another time when we got back to our original position. So the order of this figure is 2, because we had 2 places in that 0 to 360 turn that looked like the original figure. So it has an order of 2, and its magnitude would be 360 divided by 2, or 180 degrees. The center is the intersection of the diagonals. Again, the center of that figure. Now we're going to talk about plane symmetry. This is a symmetry in 3-dimensional figures, where the figure is mapped onto itself using a plane of reflection. So this was the original image we saw on one of our first slides. This green surface is actually slicing through and creating what's called a cross section of that rectangular prism and cutting it into 2 congruent rectangular prisms. So this rectangular prism is the exact same as this rectangular prism over here. That's why we can say that's symmetrical about that plane. We can see that also on this sphere, this green surface slices through the center or the equator of that sphere to create 2 identical hemispheres. In this pentagonal prism, we can see this white surface here slicing through and creating 2 congruent pentagonal prisms. And here are some more examples of plane symmetry, using that surface to cut through those figures to create 2 symmetrical pieces. Next we have axis symmetry. This is when a 3-dimensional figure is mapped onto itself using a rotation around a line or an axis of symmetry. So I have this cone that's kind of spinning. If you can imagine connecting a string from the apex of that cone straight through the center of the base and then twirling it around that string would be our axis of symmetry. And so the cone would have axis symmetry because we could draw that line through it. It's the same with this polyhedron here. We kind of have a pole running through the top and bottom here, and then we could rotate that around that figure and it looks exactly the same as we rotated a certain amount of degrees. Next we're going to analyze a couple of shapes and see whether we have plane or axis symmetry, both or neither. So we have this L-shaped prism. Notice we could have a surface that goes through the center of the L to create 2 symmetrical L-shaped prisms. So this figure does have plane symmetry. Notice there's not a line that we can draw through that though, where we could rotate that figure and create a symmetrical image. So there's not a line that we could draw through here and rotate that figure and it look exactly the same. So it does not have axis symmetry. Here in the regular pentagonal prism, if we were to again slice through the center of the lateral edge on each of those lateral edges, we would have plane symmetry. Or we could draw a surface straight down through this middle of both bases, and we could create plane symmetry that way. We could also create axis symmetry through the center of the bases. So when we draw that line, we could rotate that figure and that regular pentagonal prism would look the same as we rotate around.